Hey all. So I thought I'd give a little bit of an update, and I'm having some fun with this 4-inch rotor with these strong magnets on it, and I've looked at a number of things. So I'll just tell you what the circuit is you have a coil. In this case you have two coils in series, and you have a reed switch. I got rid of the whole Arduino thing, so you know those you can't really see them, but those resistors aren't doing anything. All you got is the reed switch. I'm getting simple, and so the reed switch goes to a transistor. In this case, it's set up PNP, so the reed switch is going to a PNP, and then the coil pulses through the PNP. And the one thing that I do have set up is got a backwards diode off of the positive. We're backwards here, so with the PNP, so off of the positive, and then I just have a resistor set up. I'm not gathering it, but I am shunting it so that I don't have to worry about, if I go higher in voltage, blowing out the transistor. And later I'll also look at, with these arrangements, you know, how the radiant behaves with different setups as well. But the things I've kind of looked at, I've looked at one coil, I've looked at two coils. When you add another coil, it's like all hell breaks loose, figuratively speaking, of course. But when I put it in parallel, I don't know what the heck's going on. And, you know, I believe John Bedini kind of even referred to this like he'd be showing it to, you know, people from Boeing or whatever. And, you know, I mean, I never read the textbooks, but if I had the textbook and I read it, I'd throw it out the window. So that's about where that is. It's not normal. I mean, it's not at all just when you put it in parallel that the amp draw doubles or anything like that. It's strange. And then when you put it in series, it doesn't behave exactly how you'd expect either. And the first thing that I looked at, you know, when you have one coil and you're putting it here, depending on where you're timing it, you know, you just move the coil around. You're leaving the reed switch there in the same place. The amp draw will vary fairly dramatically, and also the rotational speed will. And of course, you know, everything's easy until you start. And one of the things that I've noted as I've gone along here is that the freewheel rotational speed, the maximal freewheel rotational speed, is not necessarily where you have the maximal torque. So that's another thing. And then you have that the amp draw varies because of the interaction of this magnetic flux with pulsing of that magnetic flux. And so it's hard to figure out exactly where you want the coil, and that's in a conventional setup like that. So what I've looked at so far, I've looked at the coil set up this way. I've looked at one, I've looked at two. I've looked at them in parallel, I've looked at them in series. I'm going to go with series. I've looked at the coil this way, 0-4 style, and it's nearly the same. I think it's a little bit worse, but it sure sounds cooler when it spins up. I don't know why, it just does. I've looked at these coils without iron cores and with iron cores. I don't think, once the magnets get this strong, I don't think an iron core helps you. And seeing, you know, kind of the homebrew situation that I'm working with, it sure is nice not to have the iron cores, because of course if I had the iron core there, boom, that's what you would be stuck with. You'd have to be holding it there, you'd have to figure out the exact spot. And then, as I said, there's those other variables that you're trying to figure out. Where's the maximal freewheel rotational speed? Where is the maximal torque where is the point where the amp draw is lowest per the torque that you're getting out, not the freewheel rotational speed that you're getting out. So as I said, I've looked at it, and I don't think there's much improvement with an iron core. And the reason for that, I think, is as follows. Let's say you put an iron core in there, and it strengthens this electromagnet, the B field of the electromagnet, tenfold. If you had a really weak magnet here, it wouldn't make that much difference. You would just primarily be seeing the increase in strength here. If you have a strong magnetic field, when this comes in, let's say this is north facing, in the iron core it generates a south facing pole so that the two attract, and of course it wants to just boop like that, and it creates that resistance which is cogging. Now, no matter what the strength of this magnet is, whenever you put the iron core in, you're going to get, say, a 5 or a 10-fold increase in the strength of your electromagnet. However, when you have this strong permanent magnet, if you put it there, the thing's not going to spin at all. And you will get both maximal torque and maximal rotational speed moving it out. So let's say you made the magnet 10 times stronger. You're still only going to get the same improvement in this, but the resistance here will increase tenfold, so you'll have to move it out here, and so you're right back where you started. There's no further improvement. And the nice thing there is, without the cores, you know, as I said, with this kind of homebrew system, I don't have to worry about, you know, these things moving all over the place. I can position them a bit. So the other thing I looked at, besides different arrangements of the coil and whether there's a core or not, I used this as a pickup coil, and I used it with an iron core, without an iron core, facing sideways, facing forwards, and again looked for where I thought things were best. So when I spin it, this thing will probably look pretty neat, but I'll say at the very, all right, I'll say with like one coil, the worst that I did was it was 3% efficient, and I've managed to get it to 12.5% efficient. So that's not real good, but it's 2 doublings and another 12.5 to 25 to 50, well, 3, and you're there. So that shouldn't be a problem. So again, I just put a bridge rectifier on this, and then I would move it close with an iron core or without an iron core. And then, you know, the other question is, how much do you want it to introduce drag? Because, you know, if it introduces too much drag, I mean, eventually the rotor would just stop. There'd be no magnetic flux. If it hardly introduces any drag, then there's so much distance that it's not seeing any significant flux. So you want to figure out how much you want to slow the rotor down as you're dragging off power. So let's just make the thing spin. So, I mean, I just kind of threw these in there. You know, you'd want to hunt around for the sweet spot, but let's see what it does. And we're at 10 volts. So it's not a lot of torque, but there's a little less torque setting it up Z-force style. But away it goes. And so we're drawing 1.7 watts. And, you know, when you have it dialed in the 0-4 setup, it just keeps increasing. More so, you know, it's easier to get it dialed in than, you know, when you have it conventional setup, if you're off by like a millimeter between the two coils, they'll kind of interact a little bit and not be as additive. But this is, let's see if I can show what it's spinning at. That's not it. 1500 RPMs. And it's still climbing. So, I mean, it doesn't sound like much, but that's a 4-inch rotor, so if it was a half-inch rotor, you would times it by 8. So that would be like 1200 RPMs on a little half-inch rotor. I've run the thing up to 15 volts, and I think even 20 volts, but only adding resistance, because the thing, you know, I'm like, you know, sitting, I need to wear a cup or something, because it gets a little bit scary. But things go better at higher voltage, both with this, what you're gathering, and also with the radio. So you would want to run it at higher voltage. But the thing I have, let me shut this down. Isn't that sweet? Oh, and if I turn it sideways, it would draw a little bit less. I mean, turn it conventional, it would draw a little less. So let me just say a few more things and then I'll shut up. I lost my train of thought. Oh yes, so the first things, I have some 26 gauge wire on the way, and especially like with these air cores and whatnot, and you think about, you know, the magnetomotive force is ampere turns. I can't really figure out why, and in fact I don't think there would be any problem why with going with smaller gauge wire. The kind of things that you see here where the amp draw varies depending exactly where you have it, and the torque varies and whatnot, that'll probably be amplified with thinner wire, but who cares? You set it up right, you figure out where it's going to go, and then you nail it in, figuratively speaking, but you set it in, you know, so it's not going to move. The other question, and this is one that I really want to get to the bottom of. Let's suppose either running this conventional style or zero force style, that you had a second magnet just like that one right there, and this coil became more oblong or oval. I mean, really, you would just want it like that, and then, you know, and then the round part there. And I think ideally what you would want would be a rectangular magnet. So what I'm getting at is that you would have just the wires like that, and that should give you the most direct lines of force in the direction that you want, because with all of this circular stuff, I mean, this is what's doing the work, would be my guess. I mean, this is contributing a bit, and this isn't doing a damn thing. Sorry. So if you had it further up like that, and more of the wire like that, I think that would be more efficient. But that's really the thing that needs to be resolved. Not resolved, it needs to be looked at. Because if adding another magnet there, like that, and having a coil that's shaped more oblong, does double the torque for the same input, and, you know, hell, you can make the thing 10 yards you can make it 10 yards long, and so that needs to be nailed down. And the last the last question that I was mentioning again is I have some more 26 gauge wire on the way. I believe this is either 20 or 22, but I want to see how that behaves. And in all this, I haven't been keeping track of the radiant, but we'll worry about that later. Or to put it another way, that with all of these changes, what I expect, and of course, sometimes you get, surprised. But with all of these changes, what I would think would be normal with the radiant, it will improve as the speed here increases, and hence the pulse is a shorter duration, and it will also increase as your input voltage goes higher. So, one of the things that I almost don't like about this is, it would be nice to run it at 50 volts, but the thing is like scary at 20 volts. You can bring this in and slow it down, but I wouldn't want to run this thing at 50 volts freewheeling, because I think that would be something. It might hold together, but you would have one heck of a merry-go-round. Final thing, and then I'll shut up. So why don't we run it conventional style with the air core, and we're not doing anything with that. And we'll just leave this where the null field's pointing there, so that's not doing anything. And we'll run it at 10 volts. But I want to see if I can show you the variation in amp draw, depending on where you put the thing. And it changes also when you bring in the second one. It's additive. So that's where we're at. Let me see if I can find. I'm gonna let it spin up first. Okay, I think it's going to spin up. Yeah, alright. So here's there. Now I'm just moving it along the perimeter. And it'll slow down. The torque will decrease, but you've lost half your amp draw as well. And so it's like, where's the sweet spot there? And you can't go by the freewheel rotational speed. You have to bring this in and figure out where the maximal torque is. So this is it's just a heck of a lot of fun. So if we just kind of show the other coil now coming in. And then you have to find the spot where it's spinning, the amp draw is low, and you still have torque. That's probably not it. So it's wild. That's why sometimes I just want to go back to that. I should shut up now and just let this thing spin. Okay, so yeah. Alright, well, I suppose it would have been nice just to let it end on that spinning rotor, but I'll just mention one other thing, is that I'm also going to be working on an entirely different approach, and that's a magnetic ramp motor. And by that I mean, now that I have achieved novice level proficiency with 3D printing, using this 4-inch form factor, take a magnet there, have it a little indented, a little indented, a little indented, a little indented, and stop, and then on the other side have another magnetic ramp, and then you want a core, because you let the magnetic ramp go zoom, and then it wants to stay there. But all that momentum up to there was for free, and then you just pulse it. And I will say that using CDs and super glue and sealing wax and other fancy stuff, I've had one of those rotors spinning like that for microwatts. So I know that approach works, and I'm really curious to see. They weren't strong magnets. I'm really curious to see what the heck it'll do with strong magnets, because with these strong magnets, the torque when that thing is there is going to be phenomenal. The only issue with that is going to be getting a a timing wheel to time it correctly, because otherwise, you know, like half the rotor is just magnet, you know, it's just the whole magnetic ramp. And yeah, you know, you got to mention, you know, Benini showed this, and it was like an all magnetic motor. But the obvious thing was the magnetic ramp, and as I said, I've screwed around with it before, and it was really cool. So now that I can do it a bit better, you know, more easily, more precisely, and with stronger magnets, it'll be fun to look at that a bit more. So I'll sign off now. God bless y'all.